Statics, type 2 jointed rods. So in 2005 we had two uniform rods of equal length smoothly jointed at B. So when we have jointed rods, it generally involves two rods leaning against each other or are being combined somehow either at a particular point. So in this case they're jointed at the point B. Now the fact that they are uniform rods tells us that they are the same length, but they're not uniform in weight, because we can see as we read on in the question, we're told that they rest on a vertical plane with A and C on a rough horizontal ground, but the rod weight for AB is 2W and the rod weight of BC is W. So they're equal in length but not in weight. So that means that their frictional forces will be different because their reaction forces will be different. If they were equal weight and equal length, then the reaction forces would be the same, and therefore we would be looking at the same frictional forces. So because we have one is different to the other, we'll find that one rod will slip before the other. So slipping is going to occur either at point A or at point C in this case. So we're told that the coefficient of friction at both A and C is mu. And we have to basically work out what is the least value for the coefficient of friction in terms of theta necessary for equilibrium. So we have to remember that our coefficient of friction is basically the value that's going to resist this system from slipping. So we're looking for the smallest value possible that's keeping these rods in position. So let's start by marking in all of the forces acting on this system. So we're going to have a reaction force at A, and therefore if the rod AB was to slip, we would have friction in the opposite direction. We have a reaction force at C, so I'm going to call that S, and then if C was to slip, the frictional force would be in the opposite direction, so therefore that would be G. So we would expect the rod BC to slip to the right. We'd expect the rod AB to slip to the left. So again, our frictional forces will be in the opposite direction to resist that motion. We're going to have the weight of the rods. So the weight of the rod AB is 2W. So our weight always acts through the centre of gravity. And then we have the weight of the rod BC is W. So we start by looking at our up forces and our down forces. And we know that our laws of equilibrium are going to state that our up forces must equal our down forces when the system is in equilibrium. So our up is R and S, and our down is 2W and W. So that means that R plus S must equal 3W. And we can't say that our left equals right in these cases here, because that would assume then that these two frictional forces are going to be the same. And we know that F is equal to mu R and G would be equal to mu S, but R and S are not going to be the same because these two rods have a different weight. So we'll go to our next law, which is that some of the moments around any given point must be zero. In other words, some of our clockwise moments must equal the sum of our anti-clockwise moments. So in getting our moments, we need to decide where we're going to take our fulcrum. So we're going to start by looking at the system, and I'm going to take my fulcrum at the point A. So I'm just going to mark that with a star there. So therefore I need to look at what forces will make the system go clockwise and what forces will make the system go anti-clockwise. So if I'm looking at the reaction force R and the frictional force F, because they are at the fulcrum A, that means their perpendicular distance is 0, and therefore they will have no turning effect on the system when the fulcrum is at A. If I look at 2W, that's going to pull the system in a downward direction, and therefore that will make it go in a clockwise direction. Same with the W. If I was to pull on that system, it would make it come down and therefore go in a clockwise moment. And if we look at G, G is along the line of action and therefore has no perpendicular distance. So therefore that has not got any turning effect on the system. If I look at S is pulling the system in an upward direction and therefore will have an anti-clockwise moment. Okay, so we're going to have 2W is a clockwise moment, W will be a clockwise moment, S will be an anti-clockwise moment, and G is along the line of action, so no perpendicular distance to A and therefore no moment. And I'll just make a note then that R and F have no perpendicular distance. So now what we need to do is work out what are the perpendicular distances for 2W, W and S to the point A. So I always like to draw a little quick diagram. So if I'm looking at 2W, well, here's A, that's my fulcrum. My 2W is acting from the centre of gravity of the rod. We're told that the rod length is L in this case. So if we're not told what the rod length is, it's always nice to take it to be 2L, because then if we're going from the centre of gravity, then it'll just be L and L. So because we're given L on this diagram here for AB, that means the halfway point is going to be L over 2. So that's going to be L over 2 to A. We know that the angle here is 2 theta, ABC. So if I was to divide that triangle into two triangles, then that would be the angle theta and the angle theta. So in other words, this angle here is going to be theta. So therefore, if my weight 2W is acting along this line here, then the perpendicular distance from the line of action of the force to the fulcrum would be this distance here, which is the opposite in this right angle triangle. This is my hypotenuse, and this side would be my adjacent. And therefore the opposite is always h sine theta. So h in this case is my L over 2, and sine theta is the angle. If I look at the next clockwise moment, it's the weight of the rod BC. So again, if I mark here is my fulcrum A, well, I have the rod AB and then the rod BC. So the weight is acting along this line here, and therefore I need to get the perpendicular distance from the line of action to the fulcrum. So therefore this would be the perpendicular distance. So again, if I break that triangle down into two parts, what we have here is theta, and this angle here is also theta. So again, this is going to be the opposite, and this side will also be the opposite. So that's h, which is L, and then this triangle here will be L over 2 and L over 2. So we'll have h sine theta, so that's going to be L sine theta for the first half of the triangle, so the triangle AB down to this midpoint here. And then for the second triangle, this little bit here is my opposite. So again, that's going to be L over 2 sine theta. So in other words, if I combine these two together, I have L sine theta plus L over 2 sine theta, which is 3 over 2 L sine theta. If I'm looking at the anti-clockwise moment, I'm looking at the reaction force at C. So again, I have my fulcrum point A, the rod B, and then down to C. So therefore, the reaction force is this force here, S, acting up. And therefore, the perpendicular distance from the line of action of the force is going to be this line here. And if I know that this angle is 2 theta, then again, if I was to split that triangle into 2 right angle triangles, then this would be the angle theta and the angle theta. This side would be the opposite. This side would be the opposite. My adjacent is the perpendicular height there, and the hypotenuse is the length of the rods, which are both L. So therefore, if I'm looking at the opposite side, well, the opposite is always h sine theta. So the hypotenuse in this case is L sine theta. And the base of the second right angle triangle there would also be L sine theta. So therefore, the perpendicular distance from the line of action of the force S to the fulcrum A is going to be L sine theta plus L sine theta, which is 2L sine theta. So again, always working out your perpendicular distance using your trigonometry and your right angle triangles. Okay, so now we have our perpendicular distances for our clockwise moments and our anti-clockwise moments. And again, I'll always draw these diagrams just to help me work those out. In an exam situation, you can obviously just go straight to your formula and subbing in force by perpendicular distance. So in other words, we will have to remember that our moment is our force multiplied by our perpendicular distance from the force to the fulcrum. So if I'm doing my clockwise moment, my force is 2W. Perpendicular distance I worked out was L over 2 sine theta. Clockwise moment W for the force. Perpendicular distance we worked out was 3 over 2L sine theta. And that must equal the sum of the anticlockwise moments. And we only have one anticlockwise moment, where the force is S and the perpendicular distance to the fulcrum A is 2L sine theta. So just remind myself that my fulcrum was at A. So it's always important to let your examiner know where are you taking your fulcrum so they understand, have you got the correct perpendicular distance. So anything common across there? Well, I can see I can divide across by L, L and L. I can divide across by sine, sine and sine. And then that leaves me with 2W times 1 over 2, which is just W. And then I have W times 3 over 2, so that's 3W over 2. And then that must equal 2S. So in other words, S, if I divide across by 2 there, is equal to 5W over 4. So now we have our reaction force at S. And if we go back to the first one there, or up and our down forces, we know that R plus S equals 3W. So therefore we can say that R must equal 3W minus S, which is 5W over 4. And hence the reaction force at A must equal 7W over 4. So always nice little questions once we can work out what our perpendicular distance is. So a good clear diagram is going to be always really, really important here. So we had 5 for getting out R and S, and we had 5 for setting up that first equation there. So that was 10 marks. And now what we have to do is work out what is our coefficient of friction. So we need to look at how can I do that, because we're looking for the least value of mu necessary for equilibrium. So what I need to do next is try and get mu out. So we're going to take the system and we're going to break it down into 2 parts. In other words, we're going to look at where would we have slipping. So if we look at our reaction forces S and R, we can see that the reaction force at C, in other words S, is smaller than the reaction force at A, which is R. So therefore, because the reaction force at C is smaller than the reaction force at A, and we know that F is equal to mu times R and G will equal mu times S, then we know that the frictional force at C is going to be less than the frictional force at A. So we would expect slipping to occur at S. So therefore what we're going to do is we're going to take the part of the system where slipping is going to occur first, in other words, the rod BC. So in the first case here, we had the fulcrum at A for the system. Whereas now what we're going to do is we're going to take the moments about B, so in other words, we're going to take the fulcrum at B for the rod BC. And the reason we're taking the fulcrum at B is because when we separate our rods into two separate parts, we have to remember that we would have both X and Y reaction forces. So if we have one going to the left, the other must be to the right. If we have one going up, the other must be going down. Okay, so by taking the fulcrum at B, that means that the perpendicular distance for these reaction forces X and Y are now eliminated. They would have a perpendicular distance of 0 and therefore no moment. So therefore that eliminates us having to worry about what they are. So let me erase the rod AB. So we're looking at the rod BC. Right, this is the ground. We know that this is going to be the angle theta. We know the rod length is L, and therefore if the weight is acting down, that divides that rod into L over 2 and L over 2. We have the reaction force up, which is S, and we'll have our frictional force to the right, which is G. So they're all the forces acting on the rod BC. Okay, so what we want to do is take the moments. So we're going to look at which are going to cause it to go clockwise and which are causing it to go anti-clockwise. X and Y have no moment because the fulcrum's at B. So therefore, if we look at the remaining three forces, we have W, G, and S. We can see that W is going to have a clockwise moment. And again, if I look at what is the perpendicular distance there. So here's B. So we need the perpendicular distance from the line of action to B. So that would be the perpendicular distance there. That's theta. So again, we'll be looking at the opposite. And the opposite is always going to be H sine theta. So H sine theta is going to be L over 2 sine theta for the perpendicular distance. If I look at C, I have the force G is also going to be a clockwise moment. So again, we have theta is our angle, and therefore the perpendicular distance will be here. And again, that's the adjacent, that's the opposite. And then we have the hypotenuse, where the hypotenuse is L. So therefore, because we're looking for the adjacent this time, it's going to be H cos theta. So that's going to be L cos theta for the perpendicular distance. And then if we're looking at the third force, well, the third force is S, which is going to be turning it in an anti-clockwise direction this time. So again, there's S. This is going to pull it up and around in an anti-clockwise direction. But again, we're looking for what is the perpendicular distance. Well, there's theta. So therefore my perpendicular distance is going to be the opposite. And the opposite is always H sine theta, where H is L and then sine theta. Okay, so we again have our sum of our clockwise moments equals the sum of the anti-clockwise moments. So we have our force, W, times the perpendicular distance to the fulcrum, so L over 2 sine theta, plus the force, which is G, times the perpendicular distance, which is L cos theta, is equal to the force, which is, I forgot to mark that in there, sorry, that's S, times the perpendicular distance, which is L sine theta. So again, always looking for what is the perpendicular distance from the force to the line of action. So is there anything I can divide across thereby to make this easier? Well, I can see I have an L common all the way across. And then if I multiply across by 2, That'll eliminate my fraction. So that leaves me with W sine theta plus 2G cos theta is equal to 2S sine theta. And what do we know about S? Well, we know that S is 5W over 4. So that's W sine theta plus 2G cos theta equals 5W over 4 times 2S. So if I try and get G on its own there, well, I have 2G cos theta is equal to 5W over 2 sine theta minus W sine theta. So I divide across by 2 there. And add there, and we end up with 3W sine theta over 4. And of course, if I divide across by cos, well, I get sine over cos. And of course, we have to remember that tan theta is sine over cos. So therefore, that gives me G is equal to 3 over 4 W times tan theta. So what we want to say then is, but we know that S is less than or, and therefore because F is equal to mu or and G is equal to mu S, well, if I multiply both sides here by the coefficient of friction, well, I get mu S is less than mu or, and therefore that means that my frictional force at C is less. So in other words, we say slipping occurs at C first, and therefore mu S has to equal 3 over W, 3W over 4, I should say, tan theta. We know that S is 5W over 4. And I can divide across by W, multiply across by 4, divide across by 5. And now I have mu has to equal 3 over 5 tan theta in order for the system to be in equilibrium. So we had 5 for working out what was G. And then we had 5 for figuring out that slipping is occurring at C first, and 5 for our coefficient of friction.